We want to look now at a different coordinate system than the rectangular coordinate system. It's called a polar coordinate system. We use the same type of picture here for it. And in the rectangular coordinate system, of course, you have a point x, y. And to each pair of real numbers, x and y, there's a point. And to each point, there's a pair of real numbers, x and y. Well, for the polar coordinate system, draw a line from the point to the origin. And we consider the point now to have two coordinates, the radius r and the angle theta. So corresponding to this point, x, y, is the pair r theta. And now, relating these two coordinate systems is done as follows. If this is the point r theta, then x is given by r cosine theta, and y is given by r sine theta. So if you know the pair of coordinates r theta, then you can determine the coordinates x, y corresponding to them. Conversely here, if we know x and y, then we can find at least a value of r and theta, because r is equal to the square root of x squared plus y squared, and theta, right, is the angle whose tangent is y over x. So tangent inverse of y over x gives you a value for theta. Right? Now, there are actually multiple representations of points in polar coordinates. So that, for example, in particular for the origin, 0, 0, in rectangular coordinates, if this is x, y, this is the origin. Right? As long as r is equal to 0, any number theta in polar coordinates will represent the origin. So the origin itself has got a lot of representations. Now, other points in polar coordinates, if we've got another point, say r comma theta, then if we keep the same r and we rotate around here by 2 pi, so r theta plus 2 pi, or for that matter, any multiple of 2 pi, 2n pi, this will be the same point. Right? What we also do in polar coordinates is as follows. If we looked at theta plus pi, this angle right here, then we can consider this r to be negative, and so that consequently the point minus r and theta plus pi is another representation of r theta, and for that matter, if we add any multiple of 2 pi, this will be the same point as the point r theta. So these are all the same point in the plane. Now, you want to familiarize yourself with graphing points in the plane, and eventually we're going to be graphing functions generally where r is a function of theta, where r depends on theta. So that, for example, if this is a unit of length right here, this might be the point xy equals to 1.5, 1.5, and the corresponding values of theta, this is going to be 45 degrees, and r is going to be 1.5 square root of 2 over 2, and theta is going to be pi over 4. So this is the corresponding point here. This point right here, this is the first point. This point P2 here can perhaps be represented as, this is 1 unit, r is 1, and theta is pi over 2. point over here, if r is 1.5, P3 could be represented as 0 minus 1.5 and 0. R is minus 1.5 and theta is 0, or 1.5 and pi. This point over here at radius 1, P4, 1, and what have we got here? Pi plus 1/4 pi, so 5/4 pi would be one way to represent that point P4. The point over here, say with radius 2, and well, this is an angle of 30 degrees. One way to represent this would be r is 2 and theta is minus pi over 6. So allow the angles to go back this way here also, and as many times around as possible. So that over here, this representation, theta plus 2n pi, this is for n, any integer. Likewise here. Right. So there are a number of representations. I mean, we could also represent this point P5, right, as 2 and 2 pi less pi over 6, or 11 pi over 6. So in polar coordinates as compared to rectangular coordinates, there are a number of representations for a point. Polar coordinates, of course, are going to be useful when you're dealing with something that involves circular objects or circular motion as compared to rectangular coordinates. So graphing points in polar coordinates. We now want to look at some graphs of functions, and generally here we'll be considering r as a function of theta. You clearly could have theta as a function of r. Let's take a look at one such graph. Let's say r equals e to the theta. And just as you do in, sometimes in rectangular coordinates, it's a good idea to put the various values of theta down here and the corresponding values of r. So that, for example, when theta is equal to 0, right, r is going to be 1. So perhaps 1 like so. When theta is equal to pi over 2, r is going to be e to the pi over 2. Right. E is about 3, pi over 2 is about 1.5. This is maybe about 4, something like this. Right. When theta is equal to pi, r is going to be e to the pi. Right. That's somewhere around 27. This starts to spiral outward like this and gets very large quickly, coming around and spiraling like so. We won't draw more than that part of this. Let's look at when theta is equal to minus pi over 2. Well, r is equal to e to the minus pi over 2. Right? Or 1 over e to the pi over 2, or maybe something on the order of 1/4. So this spiral now comes over here like this. When theta is equal to pi minus pi, r is equal to e to the minus pi, right? Which is quite small. And as theta goes through at negative angles here, r gets smaller and smaller and spirals around here like so. And naturally enough, the name of this curve is it's a spiral. Right. Let's look at another such spiral. Let's let r equal theta. And then again, like so, putting the value of r here and the corresponding value of theta. Theta and the corresponding value of r. When theta is equal to 0, r is 0. So like so, on that angle. When theta is equal to pi over 2, r is pi over 2. So if this is 1, theta increases like so, so it gets up to pi over 2, something like this. When theta is equal to pi, r is pi. So it continues on like so. 2, 3 units here. R is going to be pi. Right. And when theta is equal to 3 pi over 2, r is 3 pi over 2. And this continues on like so. And spirals out, getting larger and larger. Now, what about negative angles? Theta is equal to minus pi over 2. R is minus pi over 2. So when you're down at this angle right here, r is back up here again. So this spiral comes around this way like this. When theta is equal to pi, r is pi. When theta is equal to r is minus pi. So when you get over here to minus pi, r is minus pi. You get around here to minus pi. You go backwards in this direction to minus pi. And this then continues to spiral like so. And the spirals get larger and larger, meeting on the top and on the bottom each time. So here it is. Graph of r equals theta. This is the graph of r equals e to the theta. One should perhaps note that you can change these now back to Cartesian coordinates by writing square root x squared plus y squared is equal to e to the tangent inverse of y over x. Now this is the multiple valued tangent inverse. R is square root x squared plus y squared. This is e to the tangent inverse of y over x. So in rectangular coordinates, this is not a very simple function, whereas in polar coordinates it is. Same story here. All right? In rectangular coordinates, square root of x squared plus y squared is equal to tangent inverse of y over x. So here these are in rectangular coordinates. Now, sometimes it pays to look at them in rectangular coordinates to see whether or not it represents some sort of simple curve. Quite a few graphs in polar coordinates to get an idea as to how to do them. Let's take a look at, for example, r equals 1 plus cosine theta. All right. Well, this perhaps is 1. Now we've got theta, various values of r. All right. Now, here what happens with r equals 1 plus cosine theta is that this graph repeats as theta goes between 0 and 2 pi. So we really only need to graph the angles between theta equals 0 and theta equals 2 pi in order to see what this looks like. For that purpose, let's just draw a few of them. When theta is equal to 0, cosine theta is 1, so this is equal to 2. So there's a point on the graph. When theta is equal to pi over 2, cosine theta is equal to 0, and so that r is equal to 1. So this is a point on the graph. Right. When theta is equal to pi, cosine theta is minus 1, and r is equal to 0. And so this is a point on the graph. And what happens here now is this graph proceeds like so, around, and over to here like this. When theta is equal, it has to come in here with a slope of 0 because there are values all the way around here like so. And so the slope is going to be 0 as you get close to pi. the slope here. When theta is equal to 3 pi over 2, right, cosine theta is equal to 0, and so r is equal to 1 again. So this becomes 1 at this point. And then when theta is equal to pi, it returns back to 0. And the graph looks like this. And because the graph of this is heart-shaped, this is called a cardioid. All right, let's look at another here. Look at r equals cosine theta. Theta and r. When theta is equal to 0, cosine theta is 1. So the graph is over here. When theta is equal to pi over 2, cosine theta is 0. And it decreases to 0 from theta equals 0 to theta equals pi over 2. So the graph's going to look something like this. When theta is equal to pi, cosine theta is minus 1. And so as the angle goes over here to pi, this goes around through negative values till it gets to minus 1. And then when theta is equal to 3 pi over 2, right, cosine theta is 0 again, and so this goes through negative values till it gets back to 0. So what this does between 0 and 2 pi, because at 2 pi it goes back to 0, is it traces this figure here out twice. Now, you might suspect that that's a circle, and indeed it is. If we change this over to rectangular coordinates, we can write this as r squared is equal to r cosine theta, or x squared plus y squared is equal to r cosine theta, recall, is x. And so we get then that x squared minus x plus y squared is equal to 0. If we complete the square here on this by adding what? Divide this by 2, we're going to get a half. So to square a half, we're going to get a quarter. Adding a quarter to both sides, we find that we've got x minus a half quantity squared plus y squared is equal to half squared, a quarter. So what this is a circle of radius a half whose center is at the point x equals a half, y equals 0. So this is indeed a circle of radius a half. The graph of r equals sine theta, right, is also a circle, like so. It's a circle of radius a half, centered at the point 0, a half. So here are then two more graphs of functions in polar coordinates. Look at some more graphs here. Let's say r equals 1 plus 2 cosine theta. Theta and r. Now again, this is going to repeat every 2 pi, so we only have to graph this for theta going between 0 and 2 pi. When theta is equal to 0, cosine theta is 1, and so that the graph divided on the graph is 3. When theta is equal to pi over 2, cosine theta decreases to 0, and the value on the graph is 1. When theta is equal to pi, cosine theta is minus 1, so the value on the graph is minus 1. So it's back over here. Now how did it get there? Well, what happens here is it went through 0 and went back there. And this 1 plus 2 cosine theta is equal to 0 when theta, well, when cosine theta is minus a half. Right? And that's going to happen when theta, right, has a cosine here of minus a half, which is to say there or there. There's the angle theta. Theta is, if theta's cosine is going to be a half, then the picture is going to look like this, right? 1 to 2, and so this is going to be an angle of 60 degrees. So when theta is equal to, when theta is such that this is 60 degrees, or when theta is equal to pi over 3, then cosine theta is going to go back down to 0. Likewise, when theta is equal to, not pi over 3, 2 pi over 3. When we go 2/3 pi over here, theta is going to be 0. And likewise again when we go to 4/3 pi. So we really want to graph 2 pi over 3 and 4 pi over 3. And for both of those angles, the value is going to be 0. So now what's going to happen here when we go to 3 pi over 2, 270 degrees, cosine of 3 pi over 2 is minus 1. I'm sorry, is 0. Cosine of 3 pi over 2 is 0, so this is going to be at 1. So what's going to happen here is that this is going to go back to 0 here for these angles going through here. Right? And then it's going to go to minus 1 here at 3 pi over 2. And then as theta goes back to 0, that's to say as theta proceeds on to 2 pi, this is going to proceed back to 3. And so the graph of this then is this curve right here. It repeats it thereafter. And let's look at another here. R equals 2 plus cosine theta. Looks like this. Right? Theta and R. When theta equals 0, cosine theta is 1, so this is a 3. When theta is equal to, cosine theta is 1, so R is equal to 3. When theta is pi over 2, cosine theta is 0, so this is a 2, and proceeds downwards to 2 here. When theta is equal to pi, cosine theta is minus 1, so R is equal to 1, 2 plus a minus 1. So it proceeds then down like this. When theta is equal to 3 pi over 2, right? Cosine theta is equal to 0, so that R is equal to 2. And this proceeds like so. And finally when we get to 2 pi, repeats what it did at 0, it's 3, so this increases here till we get to 2 pi, like so. Both of these curves are called limesons. That's the soft C limeson. This one here is got a single interior like so. This is said to have 2 loops, a large loop and a small loop. So here are some additional graphs of functions R of theta in polar coordinates. Some additional graphs here. Let's take a look at R equals cosine 2 theta. Right. Various values of theta and corresponding values of r. Now here, since we're looking at cosine 2 theta, it's going to pay to use smaller angles here to get an idea of what's happening. First of all, let's start with theta is equal to 0. Cosine of 0 is equal to 1. So this starts out over here at 1. Now here we're going to go from theta equal to pi over 4. Because then 2 theta is going to be pi over 2. And cosine is going to go down to 0. So when we get to pi over 4, like so, the cosine is going to proceed, cosine theta is going to proceed down to 0 like this. So 0. At pi over 2, all right, we're going to be looking at cosine of pi, which is minus 1. So as theta goes between these angles here, this proceeds down here to minus 1. Like so. Theta is equal to 3/4 pi, 3 pi over 4. Right. Then when we double this, we're going to get 6 pi over 4, or 3 pi over 2. And the cosine of 3 pi over 2 is 0. And so this is going to go back to 0 here. And through negative values, as we proceed up here with the angles, right, to 3/4 pi, this is going to proceed back to 0 like so, through negative values. So for example, here is the values down here. Pi. The theta then goes from 3/4 pi to pi. Cosine of 2 pi is 1. This is going to proceed now through positive values until it comes back over here like this. Right? And then you can see what happens here. This proceeds through positive values back to 0. Right? Going around through this angle here. And then it proceeds through negative values back to 1. Going around like so. So these are theta here. And then it proceeds like so, through positive values back to 0, through negative values back to 0, going around like so, and then it proceeds through positive values back through 1, like so. And so the graph of this then is called a 4-leaf rose. By choice. I don't know why it's called a rose, but this is a 4-leaf rose, and r equals cosine 2 theta looks like this. R equals sine of 2 theta looks exactly the same, except what you'd get if you rotated this by pi over 4. Let's take a look at another here. R equals cosine 3 theta. Right, various values of theta and r. When theta equals 0, cosine 3 theta is going to be 1. So this is going to start out over here. Right. Here we're going to use smaller angles here because we've got 3 times theta to contend with. So let's look at pi over 6 when theta is equal to pi over 6. 3 times pi over 6 is going to be pi over 2, and so this is going to go back to 0. Right? This is going to go back to 0 here. Here now, we're looking at a third or a sixth of pi. We divide these quadrants up into thirds here, we can see what happens. This goes back to 0 at this point right here. Right? And then it's 2 pi over 6. Right? 3 times this is going to be 6 pi over 6, or pi, and cosine of pi is minus 1. And so this is going to when going through these angles up through here, it's going to go through negative values until it gets to -1. So through here like this until we get to -1. Right? Now 3 pi over 6 or pi over 2. Right? 3 times that is 3 pi over 2, and now this is going to go back to 0 through these angles. So as you proceed here like this goes back to 0. Right? So through positive values to 0, and then negative values to -1, and then negative values to 0. And then the next thing that's going to happen here, right here, is that this is going to go through positive values back up to -1. And it's going to go through not there, here. Positive values back out to -1, and then negative values to 0. And through positive values to 0, and then negative values over here to get to -1. And that's the first half of this. The second half is going to retrace the same steps that the first one did. That's to say, the first half circle here, this graph goes like this. Right? In the second half circle, it now returns back to 0, down here to +1, right? Back to 0, over to -1, back to 0, and over to the +1 again in the last 12th partition here. Right? So this is a 3-leaf rows. Right? Now this seems a little strange here. If we take r equal cosine 2 theta, we get 4-leaf rows. R equal cosine 3 theta, we get a 3-leaf rows that's mapped out twice rather than a 6-leaf rows, which you might expect. The fact of the matter is this, that if you look at cosine n theta, when n is even, right, you get a rows with 2n petals, or leaves. Right? So when n is even, like cosine 2 theta, you get twice as many leaves. When n is equal to odd, if you look at cosine n theta, or for that matter sine n theta, in either case, with n odd, right, you get an n-leaf rows. But it's mapped out 2 times as you go around between 0 and 2 pi, as the angle proceeds from 0 to 2 pi. So here are some additional graphs here, the various roses, cosine 2 theta and cosine 3 theta. Sine of 3 theta is just exactly the same as this, except that it is rotated so that the leaves are in here. We're going to take a look at the equation of a line in polar coordinates. It's perhaps best to do this so that it's not unfamiliar when you run across it. First of all, a line through the origin. A line through the origin is going to have for its graph, r is theta naught, where theta naught is the angle that the line makes with the x-axis. So this is an example here, right, of a line in polar coordinates. How about a vertical line or a horizontal one? So that, for example, x equals a or y equals b. Well, this is going to have r secant theta. Y equals B. R sine theta is B, or R is equal to cosecant theta times B. So R equals B cosecant theta is going to be the graph of a horizontal line. Right? In general here, the equation of a line can be given by ax plus by plus c equals 0. Right? So we can write this then as ar cosine theta plus dr sine theta is equal to 0. And consequently, well, plus c is equal to 0. So we got minus c here. R is equal to minus c divided by a cosine theta plus b sine theta. Right? This is a specific case of this. This is a case sort of unto itself here. But this is a specific case of this. And here in general, when you've got something like a constant over a cosine theta plus b sine theta, you're dealing with a line. Let's take a look at how that line gets graphed. If this is a coordinate system and this is the line right here, then what happens here with various values of theta? Well, if you start out with theta equal to 0, you get this point of the line. And as theta increases here like so, these various points of the line are plotted until you get around to the direction which is parallel to the line. When you get to that direction, then there's no point which is plotted on the line. So the points on the line continue to be plotted in this fashion here. When you get past that direction, and look at angles like so, the points are plotted back here until you get back to 0 here. Right? In which case this repeats now again for these angles here, the points plotted back here, and continues here until the angle gets back around so it's parallel to the line. In which case these are plotted back here like so, and then there's no value for this function, r here, for this particular angle. When you get past that particular angle, then the points get plotted on the line again like so until you get back to 0. So what happens here in a complete rotation is that this line is drawn twice, and there's no point for the value of theta where the angle is parallel to the line, where the line with that angle is parallel to the line. So this is how a line is plotted when in its polar coordinates. We now want to take a look at the conic sections in polar coordinates and see what their graphs look like. And actually they have got a very convenient graph. One place is the focus at the origin. And the directrix over here like so. On either vertical on this side or vertical on that side or horizontal on either side here like so. Let's consider a point xy here. Right? And this is the focus. And now so the point xy gets on the graph here. If this distance d2 times e is d1, that's to say if d1 is e d2. Right? Well, this is not just xy though, it's what? R cosine theta, R sine theta. And d1 is r. So we can start this with r is equals to e. Now, what's this distance right here? Well, if this distance here is d, like so, then this distance right here is d plus r cosine theta. Okay, so that we have got r is equal to ed plus er cosine theta, or r times 1 minus er cosine theta, subtracting this from both sides, is equal to ed, or r is equal to ed over 1 minus subtracting this from both sides and factoring r out, 1 minus e cosine theta. So this is the equation of a conic where the directrix is placed to the left of the origin. Right? If we place the directrix to the right of the origin, we're going to get r is equal to ed over 1 plus e cosine theta. Right? If we place it above or below, we're going to get respectively r is equal to ed over 1 minus e sine theta, and r is equal to ed over 1 plus e sine theta. So these two equations like so. In general, you can summarize this by r equals ed over 1 plus or minus e trig theta is the equation, where trig theta is either equal to sine theta or cosine theta. Let's take a look at a specific example with e equal to 1. We should get a parabola. Let's take a look at 2 over 1 minus cosine theta is r. r equals 2 over 1 minus cosine theta. All right? We want to draw the graph of this. And to do this, we can plot the simple angles. Theta is equal to 0, pi over 2, pi, 3 pi over 2. We want to know r. But when theta is equal to 0, cosine theta is equal to 1. And so this is not defined. There's no r there. Right? E is equal to 1 here, so we expect a parabola. Right? This is going to be the major axis of the parabola. Here's the focus right here. The directrix, what do we have? The eccentricity, this is, E is equal to 1, this is ED, so D is equal to 2. So our directrix is going to be out here at 2 units, like so. Right? When theta is equal to pi over 2, cosine of pi over 2 is 0, so r is equal to 2. So 2 here, when theta is equal to pi over 2 is a point on the graph. When theta is equal to pi, cosine theta is minus 1, so we get 1 minus a minus 1, or 2. 2 over 2 is 1, so that the value of pi is 1. When theta is equal to 3 pi over 2, cosine theta is 0 again, so we get 2 here. So here's the point on the graph at 3 pi over 2. This is going to be a parabola, and its graph is going to look like this. Here's the focus at the origin, the directrix over here at 2 units. 2 units to the left of the origin. So here it is, the general equation, ed over 1 plus or minus e times trig function sine or cosine of theta is the equation of a conic section whose focus is at the origin and whose major axis is either horizontal or vertical. Let's take a look at the graphs of the other 2 conic sections in polar coordinates, namely the ellipse and hyperbola. We call it r equals ed over 1 plus or minus e trig function of theta, or trig function of theta means sine or cosine. This is the graph of a conic section with focus at the origin and major axis, which is either vertical or horizontal. You can generally decide how to graph these things by graphing just the basic 4 points. Let's look at r is equal to 2 over 1 plus a half sine theta. Right? Here E is going to be a half, so this ought to be an ellipse. Right? ED is 2, right? So, and E is a half, so that ED is 2, D is a half, so that E is equal to 4. Huh? D is equal to 4. E is a half, D is equal to 4. Okay, so let's graph this. Plotting. We've got, we want to go through theta 0, pi over 2, pi, and 3 pi over 2. What's r? When theta is equal to 0, sine of theta is 0 and r is 2. Okay, so when theta is equal to 0, r is 2, so that's the point on the graph. When theta is pi over 2, sine of pi over 2 is 1, so we get 2 over 3 halves, or 4/3. Right? Sine of theta is 1, so we get 3 halves here, so we've got 2 over 3 halves, or 4/3. So that's part of the graph. And theta is equal to pi. Sine of theta is 0, so we've got 2 again. That's part of the graph. And theta is equal to 3 pi over 2. Sine of theta is minus 1, so we've got 1 minus a half here. Is half. Half into 2 is 4. So over here at 4, we have a point on the graph. Okay, so it's clear then, we should draw this ellipse something like this. This is one focus right here, so there has got to be another focus right over here. And the directrix here is at 4. The directrix is up here. There has to be another directrix down here that's similar to it. So here's the ellipse then in polar coordinates. Let's take a look at another. Oh, let's look at r equals 2 over 1 plus 2 cosine theta. Right. Here E is equal to 2. The eccentricity is 2, so this is going to be a hyperbola. And ED is 2, so that D is equal to 1. Directrix is going to be at 1 unit away from the origin. Let's plot some points. O, theta, and r. 0, pi over 2, pi, and 3 pi over 2. Plot the standard points here. Okay, and let's graph this here. Okay, when theta is equal to 0, cosine theta is 1, and so we've got 2/3 here. When theta is equal to pi over 2, cosine theta, so let's plot that, I guess, at 0, we get 2/3. When theta is equal to pi over 2, cosine theta is 0, so we've got 2 here. So at pi over 2, we get 2. When theta is equal to pi, cosine theta is minus 1. So we've got 1 minus 2 is minus 1. We get minus 2 here at pi. So at pi, we get back over here at minus 2. Right? When theta is equal to 3 pi over 2, cosine theta, that's cosine of 3 pi over 2, is going to be 0, and so this is going to be 2. So at 3 pi over 2 here, we get 2 again. Right. Now, this is actually going to, the graph of this is actually going to be drawn like this, and we'll see that in just a second here. Right. To determine this, let's note that the denominator here, 1 plus 2 cosine theta, is not always defined. When 1 plus 2 cosine theta is going to be equal to 0, when cosine theta is equals to, this is going to be 0 when cosine theta is equals to minus a half. So this is not defined when cosine theta is equal to minus a half. Cosine theta is minus a half at this angle over here, where this is 60 degrees. And it's also, cosine theta is also minus a half at this angle over here. Right? So at either of those two 60-degree angles, this is not defined. What this means is that these are going to be the directions of the asymptotes to this. The asymptotes are going to come up here in a 60-degree angle. And likewise down here at a 60-degree angle. This is going to look something like this. The way in which this is plotted is as follows. Here it is at 0. As the angles increase here, it follows this left-hand side around here until you get to where it's not defined here in the direction of the asymptote. Going beyond that, it's plotted going beyond that, it's plotted back on the second half here. That's to say, this angle right here is plotted back here, and further angles are plotted. This is picked up over here. All these angles coming through until you get to here are plotted back over here. This angle right here is plotted back over here. When you get to this angle, it's not defined again. And this whole right-hand side of the hyperbola has been described by these angles between, 2/3 pi and 4/3 pi. Now, when the angles pick up again on the right side of this line here, they plot the points on the hyperbola that are down here, like so. There, for example, is 3 pi over 2. And they continue plotting these points like so until you get back around to 2 pi. So the way in which this is plotted is the plotting goes up here like so, picks up down here and continues, and then comes back over here and continues, and repeats this every 2 pi. So this is a hyperbola now in polar coordinates with the focus at the origin. One of the directrices is at 1. So this is the directrix. There's clearly going to be another directrix here, and another focus over here, which can be computed real simply using the symmetry about these 2 points. I want to say something now about symmetry in polar coordinates. A graph is going to be symmetric about the x-axis, which is certainly a possibility in polar coordinates, whereas a function can't be symmetric about the x-axis unless it's 0. It's going to be symmetric about the x-axis if when r theta is on the graph, so is r minus theta. That's to say, when this point r theta is on the graph, so is r minus theta. Now, one way in which that can happen in particular, that can happen if r of theta is the same as r of minus theta. Right? But it's not necessarily for r of theta to be the same as r of minus theta for these 2 points to be on the graph for different, for example, theta plus 2 pi, r theta plus 2 pi can be a graph, and the same, likewise, r minus theta. An example where this happens, though, is really easy to observe. R, let's say, equal to 1 plus cosine theta. So, for example, here, r equals 1 plus cosine theta. The graph of this is going to be what? Theta is equal to 0. This could be a 2. Right? When theta is equals to pi over 2, that's going to be a 1. When theta is equal to pi, this is going to be a 0. Now, since cosine theta is the same as cosine minus theta, the graph of this is going to look like so. We've drawn this before. This is a cardioid, or it's an example of a cardioid. So there's an example of symmetry about the x-axis. You also have symmetry about the y-axis. But the y-axis is going to occur when r theta is on the graph. So is r, for example, pi minus theta. You're going to get symmetry about the y-axis. Okay? An example would be r equals, let's say it's 2 plus sine theta is an example of an equation. In particular, for example, if r of theta is equal to r of pi minus theta, then this will happen. But this isn't necessary. This is the condition that's necessary. If this point's on the graph and this one is, then the graph is symmetrical. Right? Here is an example where whenever r theta is on the graph, r of pi minus theta is the same point. The value of r at pi minus theta is the same, and so consequently r equals 2 plus sine theta is going to be symmetric about the y-axis. Right? What does this graph look like? Well, when theta is equal to 0, r is 2. Right? When theta is equals to pi over 2, sine theta is 1, so this is 3. Right? When theta is equal to pi, sine theta is 0 again, so this is 2. Right? When theta is equal to 3 pi over 2, sine theta is minus 1, so this is 1. Right? This looks like one of these things. Like so. And it's going to be symmetric about the y-axis. Now, for a function r of theta, you can also have symmetry about the origin, or for an equation. And this is going to occur whenever r theta is on the graph, right? So is r of r and theta plus pi. There's other ways that you can write this, huh? You can also write so is minus r and theta, huh? But minus r and theta is not likely to be on the same graph when r theta is if r is a function of theta. In fact, the only way in which it can be is if r is identically 0. But this certainly can happen. And so you can have symmetry about the origin, and sometimes you can notice that that's the case, in which case it makes graphing easier. So the various symmetries are possible for functions r of theta, or for equations that involve r and theta. I want to look now at where intersect each other. Actually, this is considerably more complicated than in Cartesian coordinates. A function f of x and g of y can intersect each other, only if f of x is g of y for a particular x. But here in polar coordinates, much more complicated things can happen. A function can actually intersect itself at a later value of theta, or for a larger value of theta. And functions can intersect in quite a few ways. I think this example will illustrate those. First of all, let's let R1 be equal to 1 plus cosine theta. Let's graph it. Right? When theta is equal to 0, cosine theta is 1, and so this is 2. Right? When theta is equal to pi over 2, cosine theta is 0, so we get 1. When theta is equal to pi, cosine theta is minus 1, so this is 0. Theta is equal to 3 pi over 2. Cosine theta is equal to, cosine theta is equal to 0, and so this is 1. The graph looks like this. It's a cardioid shape. Let's look at a second. Let's let R2 of theta be equals to 4 cosine 2 theta. Now, this has been graphed before. This is a 4-leaf rose. And it looks like this. When theta is equal to 0, this is going to be at 4. Right? So draw this, if we draw these auxiliary lines here like so, at 45-degree angles, this is going to be 0, it's going to be 4 here when theta is equal to 0. And what it's going to do is it's going to go through here like so, out over this side like this, around, back through the origin here, back out over here at 45 degrees, around, back over, up, and down, and back around like so. So, there are the two graphs. And you can see that they're going to intersect at the origin, but there are also going to be 2, 4, 6, 8 other places. This graph's going to intersect in 9 different places. All right? The first thing to do is to check the origin. Right? If either goes through the origin, if one of them goes through the origin and the other one goes through the origin, then they're going to intersect there. If both go through, then they intersect there. So check the origin and determine whether both of them go through that. Then the thing that you'd be tempted to do here would be to set R1 of theta equal to R2 of theta. And surely any solutions that you get to this are going to be places where you've got intersections. Right? In this case, surely we would set 4 cosine 2 theta equal to 1 plus cosine theta. Right? We want to solve this for theta. I'll do this in a moment. The way to get the rest of the intersections, see, that's going to produce this intersection right here because what? This graph is over here at this value theta, and this one is over here at this value theta, and so that's where the intersection occurs. Now this intersection right here, the second intersection, occurs when this angle is like so, but where's the other angle? It's back over here, huh? That's to say, this is graphed over here, much later, all right? Much later can be taken account of if you not only solve this equation right here, but you also solve when is R1 of theta equal to R2 of theta plus 2n pi, right? It's possible that R1 of theta has the same value at angle theta that R2 does, at 2n pi later. There's another possibility here also that r1 of theta is equals to minus r2 of theta plus pi. And in general here, that r1 of theta is equals to minus r2 at some value theta plus pi plus 2n pi, where n in these cases is any integer. Now this means that you've got a bunch of equations to solve here. In particular, in general, you want to solve this one here, in the general equation here, and this general equation here. If you solve these two, and also check the origin, this will find all the points where the two equations intersect. All right? They have got to intersect at something, either this form or this form. Let's solve this equation here, because that's illustrative also. We don't want to really do with cosine of 2 theta and cosine theta in the same equation here. So let's write cosine of 2 theta as cosine squared theta minus sine squared theta. Now let's change the sine squared theta to 1 minus cosine squared theta. So we write cosine squared theta as 2 cosine squared, cosine 2 theta is 2 cosine squared theta minus 1. So then we have 2 cosine squared theta minus 1 is equal to 1 plus cosine theta. Okay? That's to say what? I'm going to just use the letter C for cosine theta here now, once I've got everything changed over to cosine theta. And in general, you want to change everything over, if possible, to cosine theta or sine theta. All the cosine theta or all the sine theta. Right? So here what I've got is I've got 8c squared minus 4 is equal to 1 plus c. Or 8c squared minus c minus 5 is equal to 0. Right? Well, now this is an equation in C, a quadratic equation in C, so I can solve that. This is going to occur when C is equals to minus b, that's plus 1, plus or minus the square root of b squared 1, minus 4ac, that's plus 40, over 2a, 16. So when cosine theta is 1 plus or minus the square root of 41 over 16, you will have a solution here. So that theta is the angle whose cosine of 1 plus the square root of 41 over 16. There will be two angles like this, or another possibility, 1 minus the square root of 41 over 16. Both these numbers, it appears, are between minus 1 and 1, so they're both candidates to have an angle whose cosine is this. Square root of 41 is about, 6.5 here, huh? So that this is about a half, about 1.5, about 7.5 over 16, all right? And so you're going to get possibly two solutions, two angles theta for this. Those might be this one and this one. In fact, it looks like as if they are. Right? For the negative, or for this one here, you're going to get two other solutions. Those might be these two, but you still have more to go. So you really need to check, in this case here, some these other formulas, right, in order to determine what the other points of intersection are. Now, the thing to note is that both of these, one thing to note is that both R1 and R2 repeat every 2 pi. So you don't really, under those circumstances, you don't need to check all of these cases here. Checking this one, and this is going to give you 4 points of intersection, and this one here should do the trick. Right? So from here we presumably have found 4 of the angles where the intersection occurs. There's 4 more to go besides the origin. We now want to take a look at areas in polar coordinates, and by that's going to be meant the following. If we've got r of theta here between angles theta 1 1 and theta 2. We then got, for these numbers between theta 1 and theta 2, we've got various values r of theta. We're going to want to know what that area is between the line with angle theta 1 and the line with theta 2 and the origin and the graph of r of theta. Right? And for that purpose, what we're going to do is we're going to partition this up between theta 1 and theta 2. And for each part of the partition, we're going to end up with something that looks like this. This is theta 2 over here. We're going to want to approximate each of these little parts by a sector or pie shape, like so. And for that purpose, then, we're going to want to know what's the area of such a sector. Well, this angle here is delta theta I, or delta theta. This point right here will be r, well, the angle will be theta I. The previous one will be theta I minus 1, and we're going to want delta theta I to be equals to theta I minus theta I minus 1. So if this angle here is delta theta, then we want to know, and this is r, we want to know how much area there is here in this sector. Okay, the area of the entire circle is pi r squared. We don't want the entire circle. We only want this portion right here. And this length right here is delta theta times r. The entire circumference of the circle is 2 pi r. So what we want is delta theta times r over 2 pi r parts. We want this part of the entire area. So this is going to be the area of the sector. And we can simplify this here. The pi's cancel. One of the r's cancels here with that one. And we end up with 1/2 r squared delta theta. Right? So what this says is that if we wish to compute this area in here, what we want to do for this partition is we want to add up I going from 1 through n, I going from 1 through n, 1/2 r of phi I squared, where phi I is some angle between theta I minus 1 and theta I. We want to take 1/2 r squared delta theta I. We want to add this up, and this will give us an approximation. And if we take now the limit here, as the norm of the partition goes to 0, this ought to give us the area. Now, this corresponds to an integral, right? Recall that if you've got the limit as the norm of the partition goes to 0, summation f of wi delta xi, I going from 1 through n, this is equal to the integral from a to b, if you partition between a and b, of f of x with respect to x. So that this quantity right here is going to be equal to the integral from theta 1 to theta 2. This is our function here. So it's going to be 1/2 r squared of theta. Delta theta corresponds to the delta x here. This is b theta. So the area is given by this integral right here. You integrate 1/2 r squared theta d theta from theta 1 to theta 2. The thing to note here is since r is squared, if this area was over here, right, like so, and this was plotted out, this was r of theta, and it was negative, we would still get the same area over here. If r was negative, and this went from theta 1, this was the value of theta 1, and this was the value of theta 2. So unlike in rectangular coordinates, where if the function is negative, you get the negative of the area here, if the function is negative, you still get the area going from theta 1 to theta 2. Of course, if you go in the reverse direction, you'll get the negative. Okay, so here's the formula for the area, and we'll take a look at some examples of how to use it to compute various areas. Okay, let's take a look at the calculating the areas for several examples. Oh, let's start with r equals sine of 2 theta. The graph of this is 4-leaf rows. Theta is equal to 0. It starts at 0. And the graph looks like this. This part right in here is plotted between the angle 0 and pi over 2. And so we ought to be able to find the area of this by taking the integral from 0 to pi over 2, 1/2 r squared, which is to say sine square root of 2 theta d theta. Right? And now for this purpose here, we want to use the fact that sine square root of theta is equal to 1 minus cosine 2 theta over 2. And so this then becomes the integral from 0 to pi over 2, 1/2. And now we've got 1/2 minus, this is sine squared of 2 theta, so this is going to be cosine of 4 theta over 2 d theta. And so an antiderivative is going to be, you've got 1/2 here still. Antiderivative is going to be 1/2 theta minus 1/2 antiderivative of cosine 4 theta. Well, sine of 4 theta, it's a good guess, but if you differentiate, you're going to get 4 times too much. You're going to get cosine of 4 theta times 4. So if we divide this by 4, that'll be right. Now we want to evaluate this from 0 to pi over 2. So when theta is equal to pi over 2, we get 1/2 times 1/2 pi over 2 sine of pi over 2 times 4 on the side of 2 pi, which is 0. So we're going to get minus 0 here. And then on the other end here, 0 and 0, so we're going to get minus 0. So pi over 8 is the answer. 1/2 times 1/2 pi over 2. Let's take a look at another here. Let's look at r equals theta over 10. This is a spiral. Right? When theta is equal to 0, it's at 0. Right? As theta increases, this spirals outward like so. Let's suppose we want this area here between these two parts. Right? Well, we can get that by computing the whole outside area and subtracting the inside area. Right? The inside area is going to be the integral from 0 to pi over 2 of theta over 1/2 theta over 10 squared d theta, huh? That's area is 1/2 r squared d theta. We want to subtract that from what happens here. This part right here is from 2 pi to 2 pi plus pi over 2, or 5 pi over 2. Again, 1/2 theta over 10 squared d theta. So altogether what we've got here is we've got 1/2 theta squared over 100, and antiderivative is going to be theta cubed over 3 times 100. Huh? So theta cubed over 300, evaluated from 2 pi to 5 pi over 2, and from this we subtract 1/2 theta cubed over 300, evaluated from 0 to pi over 2. So if we do this subtraction here, get the value at 5 pi over 2, they subtract the value at 2 pi,
take the value here over at pi over 2, subtract the value at 0, and then this is going to give you the area between here, between this, and between 0 and pi over 2, between these two angles. So there are two examples of computing areas. Now let's take a look at another example of areas here in polar coordinates. Let's look at r equals 1 plus 2 cosine theta. All right. Let's see what this looks like. When theta is 0, what's r? Cosine theta is equal to 1, and so r is going to be 3. Like so. When theta is pi over 2, cosine theta is 0, so r is going to be 1. So, when theta is equal to pi, cosine theta is equal to minus 1. So r is going to be minus 1. 1 minus 2. So it's going to be back over here. When theta is equal to 3 pi over 2, cosine theta is going to be 0. And so r is going to be 1 again. So it's over here. And recall that the graph, we've really done this, looks something like this. All right. And to complete the picture here, we want to look at when is this equals to 0. And it's going to be equal to 0 when cosine theta is equal to minus a half. That's to say, when theta is equal to 2/3 pi or 4/3 pi. Right? At 2/3 pi, well, this is 60 degrees in here, or at 4/3 pi, this comes into 0. And so the graph is like so, with an outside loop, a large loop, and a small loop. And let's suppose that we want to know the area in the big loop, excluding the small loop. Right? Well, if we compute around here, like so, we're going to get both the big loop and the small loop. What we want to do is we want to subtract from that the area of the small loop. So, what happens here? Well, if we started at minus 4/3 pi and went to 2/3 pi, this would give us the area of the big loop. I'm sorry, minus 2/3 pi to 2/3 pi. Because this is plotted from minus 2/3 pi all the way around here to where you get to 2/3 pi. So we would want to look at 1 plus 2 cosine theta, quantity squared, times a half, d theta. We want to subtract from that the integral from 2/3 pi to 4/3 pi of the same function. 1 plus cosine, 2 cosine theta, quantity squared d theta. Right? Now we really could, because of the symmetry, we really could double this and go from 0 to 2/3 pi. So let's do that. 0 to 2/3 pi. And we don't have to worry about the half here because we're going to double that. And then, now when we multiply this out, we're going to get 1 plus 4 cosine theta plus 4 cosine squared theta. Right? We're going to subtract from that the integral, but from 2/3 pi, we really could go, we should have a half out here, we really could go from 2/3 pi to pi and multiply that by 2, because that would give us this area here times 2. So we could do that, and we'll remove the half from here. So if we go from 2/3 pi to pi, the same quantity here, right? 1 plus 4 cosine theta plus 4 cosine squared theta. D theta. Right. And antiderivative cosine squared theta is equals to 1 plus cosine 2 theta over 2. So we're going to want to antidifferentiate this, we're going to want to antidifferentiate this. For an antiderivative, then what we're going to get? The antiderivative of 1 is theta, right? Plus 4 antiderivative of cosine theta is sine theta. And then we've got plus a half. Antiderivative of a half is half theta, so we're going to get 3/2 theta. Then we've got plus a half. Antiderivative of cosine 2 theta is going to be sine of 2 theta over 2. So we want to evaluate this from 0 to 2/3 pi and subtract from that what we get if we evaluate it from pi, 2/3 pi to pi, and that'll give us the area. Right? So all that's left really here is to put these numbers in. This is going to be, as before, 3/2 theta plus 4 sine theta plus 1/4 cosine 2 theta, cosine sine 2 theta. Right? All that's left here is to put the value of this at 2/3 pi and subtract the value at 0. And then similarly put the value in here at pi and subtract the value at 2/3 pi with a minus sign in front of here. Right? Doing that carefully will give you the area of the outside loop here that is not in the inside loop. That's to say it's this area out here. Okay, so there's another example involving areas. Let's take a look at another example. Let's let R1 be 1 plus 2 cosine theta. Let's take a look at the graph of this. Okay. Theta, R. When theta is equal to 0, R is 3. Cosine theta is 1, so R is 3. When theta is equal to pi over 2, cosine theta is equal to 0, so this is 1. When theta is equal to pi, cosine theta is minus 1, this is back here. Right? When theta is equal to 3 pi over 2, cosine theta is 0, so we get 1. So it's back over here. This was just graphed recently here. It looks like this. Right? This is a 2/3 pi. Right? And this is a 4/3 pi. We're at 0. Let's take a second curve here. R2. Oh, let's be easy here. R2 of theta is equal to 2. Right? It's the circle radius 2. Now suppose we want this area right over here. The area that is outside the circle but inside this. Right? Well, we're going to want to find out where these two intersect in order to compute it. Right? So when is 2 equals to 1 plus 2 cosine theta? This will allow us to compute it here. Right? It's when what? 1 is equal to 2 cosine theta, or when cosine theta is a half. Right? Cosine theta is a half. When this is 1 to 2 here, let's say when theta is equal to 60 degrees, or pi over 3. Right? And minus pi over 3 will be these two angles here. So what we want to do is we want to integrate from here to here. We want to integrate minus pi over 3 to pi over 3, 1/2. The outside one here is 1 plus 2 cosine theta squared d theta. We want to subtract in the inside. We can just continue to do this here by subtracting the second one squared, because it's between the same angles here. So 2 squared d theta. Right? And the symmetry here will actually allow us to go from 0 to pi over 3 and multiply by 2. So if we get an antiderivative here, it's going to look like this, right? This is going to be the integral from 0 to pi over 3. What? I guess 1 plus 4 cosine theta plus 4 cosine squared theta. Cosine squared theta is 1 plus cosine 2 theta over 2, and we've got minus 4 d theta. Right? And antiderivative is going to be theta plus 4 sine theta plus 4 halves is 2. So we're going to get another 2 theta, so 3 theta altogether here. And then we've got 4 halves is 2. Then the derivative of cosine 2 theta is going to be sine 2 theta over 2. So we want to evaluate this from 0 to pi over 3. Right? Doing so is going to give us the answer. Right? That's the same. Take this at 3 times pi over 3, 4 sine of pi over 3, 2 sine of 2 pi over 3, and subtract the values at 0, which is 0 throughout. Right? So what you're going to get for an answer here is going to be 3 times pi over 3, which is going to be pi, and then sine of pi over 3 is square root of 3 over 2. So we're going to get plus 4 square root of 3 over 2. Sine of 2 times that is also going to be square root of 3 over 2, so we're going to get plus another square root of 3 over 2 for 5 of them all together. And so the answer to this area is pi plus 5 square root of 3 over 2. This, the evaluation of this integral, this between 0 and pi over 3. Sometimes when you've got a graph in polar coordinates, r of theta, it's desirable to be able to determine the slope at a particular point here. That's to say you want to find dy dx. At theta, r of theta. And this can be done very simply using the chain rule. That's to say, dy dx is equals to dy d theta over dx d theta. Right? dy dx times dx d theta is dy d theta is nothing but the chain rule. So if we start with y, which is r of theta sine theta, this is y of theta then, and x, which is r of theta cosine theta, then dy d theta is a product. So the derivative is going to be sine of theta as the derivative of r plus r times the derivative of sine of theta, which is cosine of theta. And dx d theta is cosine of theta times r times the plus r times derivative of cosine theta, which is minus sine theta. Right? So that dy d theta over dx d theta is going to be r prime sine theta plus r cosine theta divided by r cosine theta minus r prime cosine theta minus r sine theta. So this is dy dx at theta. All right. Sometimes this formula is also given by dividing numerator and denominator by cosine of theta, in which case we get that this is equals to r prime tangent theta plus r over r prime minus r tangent theta. This is another formula for dy dx theta. All right. This is just a little bit more general in the sense that this one right here is not defined when cosine theta is 0, and this one very well may be. However, either of these two formulas then give you derivative of y with respect to x at a point theta r of theta. They're not worth memorizing because you can easily derive them by keeping in mind that what you've got to deal with here is the chain rule, and so consequently this is going to give you these formulas. I want to mention one more formula which I'm not going to derive at this point, although we could really with considerable effort, and that is the length of the graph between theta 1, the angle theta 1, and the angle theta 2. The length of the graph is given by the integral from theta 1 to theta 2 of the square root of r prime of theta squared plus r of theta squared d theta. Right? It would be possible to derive this at this point, starting with the length of the graph for a function of x and using dy dx here and making some substitutions. But it's really easier to do this with more machinery. And so this will be derived later. But at any rate, the formula for the length